back for the second session. So in the previous session, we have learned how to obtain an equation for the periodic extension of x of n that is represented by xp of n as given by this particular equation. What you must note is, knowing the value of the samples of the spectrum x of omega, one will be able to reconstruct xp of n. If I have to reconstruct xp of n, all I need is to what? Collect the samples of the spectrum x of omega, that is nothing but x2 pi k by n. And once I know xp of n, obviously I should be able to retrieve x of n from xp of n. How is that? Since we know that x of n is said to be periodic, is said to be what? Periodic extension of x of n, because x of n is said to be what? Getting itself repeated periodically for every interval of n. Based on that nature, I should be able to recover x of n from xp of n by considering xp of n for one period, For this, there is a prerequisite. The prerequisite is that whatever sequence x of n I'm initially going to subject it to Fourier transformation, that particular length of that sequence is designated by variable L. Okay, and for the proper reconstruction, that value of n, which refers to the n samples, n frequency samples in the frequency spectrum, that value of n should be either equal to L or greater than L. Only for this particular condition, the reconstruction is said to be perfect, because for this particular range, n equal to L or greater than L, it's found that the discrete time signal x of n is exactly equal to xp of n. If I could choose the value of n, the number of samples, to be less than the length of the finite duration sequence x of n, it results in aliasing effect. Whatever I told you has been shown in the figure over here. Consider the discrete time sequence x of n. If you could measure the value of L starting from indexing 0, 0, 1, 2, 3, 4, 5. The value of L will range from 0 to 5. The value of L is assumed to be 5 in this case. While assuming the xp, while observing the waveform xp of n, it's found that here I've chosen this value of n to be very much greater than the value of L. The value of L, what we have initially assumed, is to be equal to 5. If you could check the value of n, 0, 1, 2, 3, 4, 5, 6, 7, 8. Comfortably, the value of 8 is very much greater than 5. So if I could consider xp of n for any one single period starting from 0 to 8, I should be able to perfectly retrieve x of n from xp of n. Conversely, if I could choose the value of n to be less than the value of L, in this case, what is the value of n? 0, 1, 2, and 3. The value of 3 is less than 5. L was the length 5. Since 3 is less than 5, for this one single period, I cannot reconstruct back my original discrete time sequence x of n, because just following the first period, the second period samples are also occurring. But whereas my length L in the original sequence ends somewhere till here. But whereas in this sequence, you can observe that the samples of one period will get what? Overlapped on the samples of the second period, which results in aliasing. That is why I cannot faithfully reconstruct back the signal x of n from xp of n. So to conclude, it's found that for the duration n varying from 0 to n minus 1, the discrete time signal x of n is equal to xp of n. Outside this range, the value is 0. The summary is: initially subject x of n to Fourier transformation. I get the spectrum x of omega, which is said to be continuous in nature. In order to overcome this drawback of continuity, what I do is I do the sampling in the frequency domain. I try to collect the samples. By obtaining the samples of the frequency spectrum, I will be able to retrieve the signal xp of n. Once I get xp of n, from xp of n, I should be able to get back my original signal x of n, provided the value of n is either greater than or equal to the value of capital L. If I could choose the value of n to be less than capital L, I will not be able to reconstruct x of n from xp of n. So once I know x of n, I can use this particular equation to get an equation for x of omega, or the continuous frequency spectra, if it is desirable. Okay, again I'll stop it over here. Okay, this is the second video session of derivation 1. I'll stop it over here, and again for the next derivation there is another video which will be uploaded. You can kindly check out that. Thank you.